Hi class, we are now on 11.5, Charles's law. This is dealing with temperature and volume. So if we increase the temperature of a gas, then the kinetic molecular theory states that the motion of the gas particles will also increase. So basically, temperature increases, the motion, the energy also increases. If the amount of pressure, we keep the amount of the moles and the pressure constant, the volume of the container will increase. So basically, dealing with volume and temperature, and if one increases, the other also has to increase, and if one decreases, the other one has to decrease. We are not concerned with pressure or the amount of gas. They are held constant. So if we look at a pressure of a gas sample, keep the pressure of the gas sample constant and measure its volume at different temperatures. So what do we mean by constant? Constant means that the pressure doesn't change. So we have to have an adjustable door. So as the pressure will try to increase, we can expand this out more and more. That will keep the pressure constant, even if the volume is increasing. So in this case, we see as temperature increases, we see that the volume also increases. Now here we have absolute zero temperature. Absolute zero refers to there are no other temperatures that exist out, below zero when we're dealing with Kelvin. Kelvin does not, we do not go below zero Kelvin on here. So also one more thing, when you hear the word absolute, that is referred to Kelvin. The word absolute tends to be, it's pointed towards Kelvin. Okay, so in Charles's law, the Kelvin temperature of a gas is directly related to a volume. That means when one goes up, the other one also goes up, or if it goes down, the other one also goes down. Pressure in moles of gas are kept constant. When the temperature of a sample of the gas increases, it means its volume also increases. So what does this mean? Well, this means that here is the formula, and if we look at this situation, these conditions right here. So in this case, we have a T1 is 200 K and V1 is 1 liter. And the final conditions is T2 is 400 K and V2 is 2 liter. So what has happened is that T1 has doubled, so we expect the volume to also double by the same amount. And it does. So this one is a smaller container, and as the temperature increases, the volume also increases. It has to increase if we keep this at a constant pressure, because if we kept it as this, the pressure would increase. So it has to have some movable door or some movable valve to allow this to keep expanding to keep the pressure constant. All right, so this is just showing how to move things around if you needed to solve for V2. Just gives you an idea to be comfortable solving this and moving things around. Sometimes it's easier to solve it before plugging in the variables so that you can just plug in directly and it's already been situated the way it needs to. Okay, so this law was founded by J.A.C. Charles. He was the first to quantify the relationship between volume of a gas and temperature. And as you can see, the volume is proportional, that's what this means, is directly proportional to the temperature, while the pressure and the amount of gas stays constant. So this is basically what I've been saying the whole time. If two variables are directly proportional, then increasing one by some factor increases the other by the same factor. When the temperature of the gas is doubled, its volume doubles. When the temperature is tripled, its volume triples, and so forth. So if we look at a balloon and we put the balloon in ice water, you will see that it will deflate because the molecules have the energy taken away. They slow down tremendously, and so this balloon deflates in the ice water. However, if you take that same balloon and put it in cold water and boiling water, the boiling water will transfer that heat to the balloon and allow as the temperature increases, the volume is going to increase because those molecules now, gas particles, have energy to move around, and they will keep having collisions with the surface, and that'll allow the pressure to, not the pressure, but the walls, it'll allow them to have more energy, and the balloon will inflate. Okay, so let's do some problems. A sample of gas has a volume of 2.80 liters of unknown temperature. When the sample is submerged in ice water at T equals 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature? Assume a constant pressure. So this is asking for two. It's asking for the temperature, and it's asking for it in kelvins and Celsius. So we need two answers. We'll get the same value, but then we need to convert it back to Celsius. So we have V1 and V2, and then we take the temperature of T2, and we need to get both 0 degree. We need to get Celsius and Kelvin. So we need to know what we're solving for. In this case, we're solving for the initial temperature. So we need to solve for T1, so we move everything around, and now we can plug everything in. First thing you should always do, though, get everything out of Celsius right away. If you forget, you'll plug in Celsius and your answer will be wrong, and you handled the problem wrong. So even if you knew how to do it, you get no credit because you didn't answer it correctly. So, and I can only go by how you answer the problems. So in this case, we change T2 to Kelvin and we plug in Kelvin only. So when you remember, when you're answering problems with temperature, Kelvin only. So we get our answer in Kelvin, but we're not done. We also need it in Celsius. So we go back and we minus the 273, and that gives us 24 degrees Celsius. Remember how to go from Celsius to Kelvin. We add 273 to the Celsius, that gives us Kelvin, and when we want to get to Celsius, we subtract 273, and that gives us our Celsius. All right, so a balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon at constant pressure and moles? So in this case, first thing to always do, change it out of Celsius to Kelvin. And then we look for our variables, and we should look at the trend to understand what's happening. In this case, if the temperature is decreasing, then we expect the volume to also decrease. So in this case, it should, and if we plug everything in, it does decrease, so our trend is correct. So we end up with 729 milliliters. A sample of oxygen gas has a volume of 420 mils at temperature of 18 degrees Celsius. At what temperature will the volume of the oxygen be 640 mils? So in this case, same thing. We're going to convert anything that's in Celsius right away, and then we plug in everything that we know. And we solve for this, and it's asking for it in Celsius. So there's a space here that shouldn't be there. We have it in Kelvin, but we have to get it back into Celsius. So we end up with our answer of 443 Kelvin. But if we subtract the 273, it gives us our final answer as 170 degrees Celsius. And that's it.